So this leads now to discussing the vectorization of both the for loops, if else statements, and the mathematics behind it. Now, again, just like before, this is even if you've done programming before, this takes a little time getting used to. But once you get the hang of it, it's a very powerful concept and very powerful tool in programming. So when I was in my MQF program, I wrote a program in Java to find a minimum variance portfolio. Some of the MQF students, you guys know what I'm talking about. It took me about like 1,000 lines of Java code to do it because you have to do optimization and all this other stuff. In R, it takes a few lines. 1,000 lines versus a few lines. And a lot of this has to do with the power of vector mathematics, the power of vector mathematics. So in line 1, again, we have a vector A, right? Again, you guys know this. 10:1 creates a vector 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, just like you see here. Now, if I do A equals A plus 5, okay? Just like in our first couple of slides, what is going on here? Well, firstly, we have a single equals here. So we know we are either creating or transforming a data container. Done. Now, again, there's a single equals. Which side do we do first? We do the right side first. All right. So I'm going to do A plus 5. What does A plus 5 mean? A is a data container. So what does plus 5 mean? What plus 5 means is it's going to go ahead and it's going to add 5 to every element in A, right? So every element in A. And then whatever this new vector, so a temporary vector will be created here on the right side. And that temporary vector then gets set equal to A. So whatever A was before, it gets overwritten to be this new temporary vector, which obviously is the results 15, 14, 13, 12, 11, 10, 9, 8, 7, 6. Now, if I wanted to create a for loop to do the same thing, right? So if I had a for loop to do the same thing, we start off with my vector, A equals 10:1, right? I type in A, you can see that it's 10, 9, 8, 7, 6, 4, 3, 2, 1, done. Now, if I want to add 5 to every element in A, there's a couple things I need to do. First, I need some sort of tracker to track all my elements. I'm creating a new data container called CNT. And then I'm just going to iterate through every value of A, right? Every value of A for I in A. And now I'm basically going to say, okay, the first value of A is 10. And now what I want to do is I want to change the first position of A. A of CNT is what? What is CNT? CNT is 1. Therefore, A is going to be A of 1 is going to equal whatever I is plus 5. All right, and after I'm done with that line, I need to increment CNT by 1. So I'm doing basically 1 plus 1 equals 2, and CNT will be overwritten to be 2, which will move it on to the next position in the arrays, to 9. And then when CNT is 3, it'll move to 8. When CNT is 4, it'll move to 7, and so on, and so on, and so on. Going position by position, or shelf by shelf, and adding 5 to each value. When I run this, and process this, you can see now that A is now 5 is added to every number of A. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6. Just like here. Except this time, I didn't do a for loop. I didn't create any additional CNT variable. I didn't have an I iterator. No, I simply did vector mathematics. And this is why NumPy essentially what was created for Python. And this feature of NumPy, and then subsequently the pandas that was built off NumPy, is why Python took off in corporate America. And it basically took off also in the analytical world of corporate America, right? This is why. And it was done much powerful, much more faster. Subsequently, R created their own table structure, like pandas called data tables, and we'll learn about that a little bit later. That's equally as fast, in some cases faster. So This is all it. This is what it's all about, vector mathematics. So how do we, so you see the for loop aspect of vector mathematics right here. This line in 4 basically did a whole for loop, adding 5 to every element in A. Very easy. What about the conditional aspect? Well, we can apply logics directly to these. Vectors as well. I'm going to show you something here. Here, let's have a vector called b, which is 1, 5. All right. So b is going to be literally 1, 2, 3, 4, 5. Done. Now, if I were to, like same way here, if I were to simply just apply a condition to the container, b is less than 3, what does that mean? Well, just like here, when I did +5 to a data container and it added +5 to every element in A, when I do b is less than 3, it's basically going to check to see if every element in B is less than 3. And if it is or isn't, the result you get back is what we call a Boolean. Again, a Boolean is a unique type of variable in every programming language. They all got it. Even VBA, which is the fakest programming language out there. Yeah, I said it. Right? I went there, people. All right? So Booleans exist in every programming language. All right? So when we do b is less than 3, all right, we have to go through every element. So the first, number 1, is 1 less than 3? Yes, it is. Then that would be a true. And a Boolean can only be 2 variables. It's binary. There's only 2 values, true or false, in all caps. So if you see a true in all caps with no quotes, or false in all caps with no quotes in R, it's a Boolean variable, a special Boolean variable you're getting. It's binary. It can only be true or false, one or the other. All right, so 1 is less than 3, you will get a result of true back. 2 is less than 3, you will get a result true back. 3 is less than 3, no, you'll get a false back. And subsequently 4 and 5 also will give you falses. So if you see this here, and I do b less than 3, boom. See down here, the results you get back? True, true, false, false, false. And again, this is a concept called Boolean variables. Logic, right? For anybody who studied any kind of logics, this comes from the concept or mathematics of logics. All right, so how does this help us? With if-else statements? Not without using if-else statements. Well, I'll get to that in a second. Firstly, I need to show you 2 concepts before we can go any further. This concept and this concept. The C function within the brackets and the colon within the brackets. What is going on here now? Well, remember before I showed you the concept of the bookshelf? And like I said before, you can pick out any values within a vector. So even if you have a vector of, like, say, 100 values, you can grab any value. So you can grab all the values at once, or you can grab a value at one at a time in that vector. Well, you obviously, some of you guys have already been thinking about this, can grab more than one value from that vector. See, it's not just grabbing one value at a time or grabbing all the values at a time. There's also subsets of values you can get from the vector, or subset of shelves from a massive bookshelf you can get from a vector. How do you do this? There's 2 syntaxes to do this. All right. Now here, when you do colon within the brackets, notice I have b bracket, close bracket. Now within the brackets, I'm not putting just a single value. Oh no. I'm now doing 1, 3. Now, some of you guys are saying, wait a minute, 1, 3, that creates a vector called 1, 2, and 3. That's correct, it does. But when you put that vector within the square brackets, no, let me state this again. When you put that vector of numbers within a square brackets, right, of a data container, then that translates into, hey, you're explicitly stating which position of values you want back. And that is why this translates into, give me the values of b in the first position, the second position, and third position, and that's why you get the values 1, 2, 3. This example can get a little confusing, so a easier way to do it is I like to create a vector that just has some random values. Let's do 4, 34, 5, 100, and yeah, let's throw a negative there, -9, all right? So let's say this is B, all right? Now, if I said, hey, you know what? I want to see the first three values of B. The first three values of B. That's basically what I'm doing here, B1 colon 3, 1, 2, and 3. So I'm saying, you know what? Show me not just the first value, but the first, second, and third values of B. When I type this in, it gives me 4, 34, and 5. It gives me the number in the first position, the number in the second position, and the number in the fifth position. That's how you get a subset of vectors back, guys. That's how you get a subset of vectors back. All right, and this can also work like this, right? If I did B1 colon 3, what if I did B3 colon 1? All right, now you remember when I did before, earlier in the videos, 3 colon 1 gives you a vector 3, 2, 1. You put that vector of numbers within the square brackets of a data container, that translates into, okay, give me the third value back, the second value back, and the first value back. Boom. The third value is 5, the second value is 34, and the first value is 4. Hence why I get 5, 34, and 4 back. Do you see? Right? And obviously you can play with this as any way you want. You can do B2 colon 4, which will be the second value, 34, the third value, 5, and the fourth value, 100. And so on and so on and so on. All right? So that is how you get a subset of the vectors. But now let's say let's say, okay, that's great. How do I get a subset of vectors when the numbers are not next to one another? Enter the C function. And for my Python, my BAP students, the double bracket comma. This is the equivalent to double bracket comma in Python or NumPy. Right? We don't do double bracket comma. We use the C function, which is slightly weirder. But you guys will get the gist of this. All right? So let's say I want the whatever is in B, which is the fourth value and the first value, right? I want the fourth value and first value. I need to create a vector that gives me now within the B brackets, which gives me the values for essentially 4 and 1, right? But I can't just type 4 comma 1, right? Because having more than one number within those brackets, it's like, what are you talking about? There's only one dimension, right? What's this? This comma means something else, and I'll show you guys that a little later when we get to tables. So what's the right way to actually type this? The right way to type it is you have to represent these numbers as a vector. And as you guys know, the C function creates vectors. So when I put in a vector for 1 within the brackets of B, just like I did previously in lines 62, 63, and 64, now this gives me the fourth value in B and the first value in B, right? And then from there you can play with it like you want. You can play with it like you want. Give me the third position and the fifth position, the 50th position, the 99th position, etc., etc., etc. But this is what gives you complete control of the data you're getting. That not only the data you're creating, the data you're manipulating in R, but also the data you're using, or the subsets of data you're using within R. Complete control and power. This is what we're talking about here. All right? So, given this, you can also choose values not by just their positions, but you can choose values based on their actual values, the description of their values. And this is why I showed you guys this. This is where this is coming from, this B less than 3. Okay? Now, when I take these Booleans and I place them back into the data container, right? I have B less than 3. all right, which gives me false, false, true, true, false, 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 true. Okay, because 4 is not less than 3, 34 is not less than 3, 5 is not less than 3, and 100 is not less than 3, hence they're all false, but negative 9 is less than 3, true. If I pass this condition back into the data container, or even another data container, it doesn't matter, it's going to select positions for me. How does it do it? Very simple. These false, 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 and trues, whatever, translate into basically positions that you want to select. So same way before, I was explicitly selecting which positions I want using either the colon or C function. Now I'm selecting which positions I want purely based on whether the value is less than or greater than something, or even equal to something. So in this case, I'm saying, hey, go into B, grab me all the values that are basically less than 3. When I process this, the only value I get is negative 9. Why? Because that's the only one that's true. Right? As you can see down here, it's the only one that's true. So that's the only one that's going to give you a value back for anything. The ones that are labeled true will the R give you the values for. It only gives you the values for whatever is true. Hence, negative 9. So if let's crank up this, instead of B less than 3, let's say we're going to do B less than 40, right? B less than 40. Now what values am I going to get back? Right? Which ones will be true now? Let me just run the B less than 40 part inside here, just that part. And you can see I got true, 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 false, true. 4 is less than 40, 34 is, 5 is, and negative 9 is. 100 obviously is not. So when I run this now, that's why I get back 4, 34, 5, and negative 9. Because these values were all pertaining to true. They met that condition. These values met that condition. So this is Boolean slicing. This is how we slice using conditions. And ladies and gentlemen, this now with the vector mathematics is basically how we avoid using for loops and if-else statements. And the reason we do it is because, look, in R, even in NumPy, these kind of logics are optimized for speed. It's faster. It's faster to process the data like this than to use for loops. In fact, for one of my exams, one of the questions I ask is to do some sort of manipulation to the data or some sort of problem, and I will not give you guys credit if you guys use a massive for loop, right? I expect you guys to use vector mathematics because in a job interview, right? If you're breaking out with for loops, automatically your boss is going to, or the people testing you're going to know, like, this person doesn't understand the power of NumPy or R, right? By just using simple for loops. Okay, because this is faster. It's optimized for speed. So, and that is why, right, we do this. And also, it's just simpler. Once you get the grasp of it, it's just so much simpler and cleaner in terms of code. So now we get a little bit fancy here. All right, go back to the original vector, which is b equals 1 colon 5. And now I'm going to do some fancy mathematics here. All right, this is now a lot of stuff being unpacked there. So basically what's happening here is this is a single equals. So we do the right side first. All right. So the right side, we are selecting a subset of data from B. Basically, we're selecting all the values where B is less than 3. So obviously, that's just going to be this vector right here, 1 and 2. All right. Now to this subset vector 1, 2, 1 and 2, I'm adding 5. All right. So the right side now I have a vector of size 2 that's going to be just basically 6 and 7. All right. Now what I'm saying here, let's do the left side. I'm saying, hey, this vector of 6 and 7, set this equal to whatever this is. You guys never seen this before now. Now on the left side, you are basically selecting which particular values should be updated in the data container. That is what's happening here. So which values in data container B are being updated? Well, it's basically the values that are in B that are less than 3. And obviously those ones are going to be 1 and 2. What is 1 and 2 going to be overwritten to be? 6 and 7 respectively. So after I run this line, what happens is B is no longer 1, 2, 3, 4, 5. B is now going to be 6, 7, 3, 4, 5. Because 1 and 2 were chosen to be overwritten by whatever this was. And this simplified into a vector of 6 and 7. So 6 and 7 overwrote the 1 and 2 into vector B. And this is why after we execute this line of code right here, the whole thing, B now basically becomes, B basically becomes 6, 7, 3, 4, 5. All right? Taking one step further now, if we do this part right here, write this line of code, again, here's a single equals, so let's do the right side first. All right, what's happening here now? Well, here now I'm saying, okay, give me all the numbers in B that are greater than or equal to 3. Well, what's greater than or equal to 3, guys? 6 is greater than or equal to 3, 7 is greater than or equal to 3, 3 is greater than or equal to 3, 4 is greater than or equal to 3, and 5 is greater than or equal to 3. The whole thing was chosen, pretty much. And now I'm saying, okay, subtract 5 from every number that meets that condition, which is all of them. Right? Which is all of them. Oh, I think I have a typo here, guys. I never fixed this typo. Here, ladies and gentlemen, I'm sorry, I have a typo here. So this is all of them. So here I have 3, 4, 5. That's wrong. Here, it should be all of those elements. We subtract 5 from them. So if we subtract 5 from 6, 7, 3, 4, 5, what essentially do we get? We get a vector that's going to be 1, 2, -2, -1, and 0. So I literally will have 1, 2, -2, -1, and 0. And that vector of 5 values over here will be set in these positions right here. Right? And remember, when you see this on the left of the equals, you're selecting the positions that will be overwritten. So which positions are going to be overwritten? Again, whatever is greater than or equal to 3 in B, and right now that's all of them, 6, 7, 3, 4, and 5. So all those values are going to be overwritten by whatever all these values is, and now B is going to be, not this is a typo, B is now going to be 1, 2, -2, -1, and 0. All right? And then here, I end with, okay, make B plus 5. All right, so now I add 5 to everything again. So now I get 6, 7, 3, 4, and 5. And I set that to everything that is equal to B, which is B is greater than 0. Aha. Aha. All right. So at this point, what is my vector at line 8? It is 1, 2, -2, -1, and 0. Okay? 1, 2, -2, -1, and 0. Here I just say, listen, just add everything to 5. Vector mathematics. Excellent. So now I have a temporary vector on the right side. That is going to be 6, 7, 3, 4, 5. Okay? 6, 7, 3, 4, 5. But I'm saying set those 5 values equal to whatever is the left side here. Okay? But here now I'm just selecting all the values that are greater than 0. There's only going to be how many values greater than 0? I have the values 1, the values 2, and that is it. The values 1 and the values 2. Basically, I'm sorry, the first position and the second position. Those are the only numbers. Whatever numbers are in the first and second positions, they're the only ones that make the cut. But I have 5 values. So what's going to happen? You take it step by step. The first number to be the first position gets overwritten by what number? 6. Okay. The second number gets overwritten to be about what the second position gets overwritten to be what number? 7. Okay, fantastic. I have no more positions to update. So what happens to those other 3 numbers? What happens to the 4? Oh, I'm sorry. What happens to the 3, the 4, and the 5? They don't get updated. They just fall away. They disappear. Even though I had a greater number of vectors here, right? A greater number of numbers here that I needed to I needed to update I needed to basically place in different positions in B. I only served up 2 positions to get overwritten or get updated. So those 2 positions got updated by the first 2 values over on this side, on the right, and all the others numbers, they just went away, they disappeared. It's equivalent to a bus coming with only 2 seats available. 5 people are waiting to get on the bus, but a bus comes with 2 seats available. The first 2 people in line, they go. The other 3, they're out of luck. And that's what happened in this case right here in line 8, right? And for my business analytics students, in NumPy, this would have been just an error, and we have called it a day. Not in R. R is more flexible, more versatile, right? So in this case, there was no error. There was no error, right? We just ended up with a vector 6, 7, -2, -1, and 0. All right, and this is how here's the interplay of basically for loops and if else statements as vector mathematics. And I packed a lot in here. So again, in the practice test, you will see this again, and you guys will see this, but I basically hit you with all the previous slides in one slide, bam. But don't get worried if this is confusing. Go over this again, try it yourself. But in the practice sets, you'll see this again when I hammer you guys with this kind of stuff. All right, and finally, it leaves us with user-defined functions. Now, user-defined functions is not something we explicitly use in ABI, but when we have the lecture where, one, you use functions all the time. This just shows you how you can write your own function, right? But there's a lab I have, the fun lab with using RShiny, where you guys, make a little website, make a little application that allows people to interact with the data and analysis. And there, you actually, you don't, technically make your own function, but you do manipulate existing functions, or you have to fill in existing functions. So I just throw this out there just so you guys have a feel for it, because again, in every other programming language, you do define your own functions, you can make your own functions, and you use your own functions a lot at work. And again, what is a function? It's just an abstraction of code. So, for example, we have this B vector, right? Okay. There's a predefined function called sum that if I pass any vector in it, it will literally add up that data container, right? So the sum of all the elements in B is 134. I have another one called prod, and I'll give you one guess what prod does. Right? Prod is a function that literally will take all the elements in all the numbers in a vector or data container, and it'll multiply all of them together. Okay? And you have all the hits. You have max, gives you the maximum number in a vector, minimum number of vector, mean, the average of all the numbers in the vector, SD, standard deviation of all the numbers in the vector, et cetera, et cetera, et cetera. And in actuality, obviously these are the most common used functions, right? But there are obviously many, many, many functions built into R that do a lot of tasks for you very easily, right? And you guys will see this as we continue on with our lessons. Now, but how do we write our own function, right? How do we write our own function? Well, this is basically the keyword right here, right? You decide a name of a function. This is the skeleton right here. You use this keyword. You set this equal to function, parentheses, x. I'll get to that in a second. Open squiggly brace, close squiggly brace. Now, what is the x inside those parameters? Well, here, this, you decide on the name. This, you decide on the name. This is what we call the parameters. You can have one, or you don't have to have one. Or you can have many. You can have 1, 2, 3, 1,000. Doesn't matter. Whatever you want. Just like we put parameters within a function we're using, like in my example right here. Sorry. I put a single data container within these functions. We can write a function that does the same thing. That either takes a number or a data container or what have you. Right? So in this case, I just wrote a simple function that simply takes any number and multiplies it by 5 and returns it. Now, what's this keyword return? This gives you an output when you're using a function. If you don't have a return, you don't need to have a return. But if you don't have a return, you're not going to get an output out of the function. For example, this function right here, I define it once, and then I can use it as much as I want. So here I put 10. It gives me the output 50. Why? Because 10 is passed in a parameter. So 10 basically becomes x, and then 5 times x is 50. And when I return, and then it returns the 50. And so basically I get this solution. If it's 50 here, 50 times 5 is 250, output's 250. 500 times 50 is, I'm sorry, 100 times 5 is 500. So that's basically the gist of the function. All right. So here, I will write my own function. I'll call it waj equals function. And I will give it 2 parameters, not 1, but 2 parameters, a and b. Now again, waj, the name of the function, and the parameter variables, they could be anything we want. In this case, I'm going to take whatever's in the parameter of a. I'm going to create a new variable. I'm going to do 10 plus a. Create another variable in here, y equals b times 8. And then I'm going to create another variable z. That's just going to be x minus y. Right? Okay? So when I create this function, the first time I create it, I have to process the whole thing. Bam. And down here, you will see automatically when I do my functions, right? When I create that function, you see these functions pop up. Now I have no idea where A, B, and C came up. I think it's from the past. I never cleared. These are functions I wrote before. But you see my little watch function here. It's there now, right? You click on this, it has the whole definition of the function, and etc., etc. I just close that up. So now if I want to call this, I simply call watch. Now if I do this, I get an error. Why? Because this function requires 2 parameters. Do you see that? This function requires 2 parameters. Had I written a function, I'm going to call this function hello, that had no parameters, right? And you just simply call it, and we'll call this all right. And all this function does is print. You notice the hello function up there. And now if I simply just call hello, I get output high there, no error. Why? Because when I defined the function, I defined it with no parameters. When I define waj, you have to give it 2 parameters. So I will. I'll give it 2 parameters. I'll give it the numbers 2 and 10. And when I process this, boom. Wait a minute. I processed it right here, but I didn't get an output. Why, pray tell? Because there's no return. Because there's no return. But you're saying, wait a minute, hello over here function didn't have return. You are correct. But it had a print. It had a print. All right? So if I want this number outputted for me to do something with, I have to put the return. That's the whole point of the return. So now I take this, I process it, and now I'm going to do watch 2 and 10. Ta-da! Here's 68. And the beauty of this is you define the function once, you process it once, and can use it as much as you want, just like other functions. Ta-da! And so on and so on and so on, guys, right? So that's, again, a user-defined function. Again, it comes in handy a lot. We really won't really need it. You can use it to do some more problems or projects, not a problem, right? But I don't explicitly do it. I don't explicitly do it, all right? So that's basically our user-defined function. And here, oh, here's why I have the A and B, right? And here, I do a little example for you guys, right? I do an example for you guys. I basically say, okay, if this is 2 functions I defined, this is the A function I defined, right? And this is the B function I defined, 2 different functions. If that's the case, what is this going to be? I'm not going to tell you the answer. When it comes to the Q&A session, When it comes to the Q&A session, we'll go over this, and I'll see how many of you guys got it right. But go ahead and give it a go. See if you guys can get this, what the answer is, all right? Let's see if you guys give it a try. All right, and then finally, we'll end on this slide, the list containers. Now, here I finally teach you a new data container called a list. And the list is a very interesting data container. The list is basically, and here we will see list data containers in our other labs or future labs. Here the list container basically is a data container of data containers. Now, if you recall, I told you the basic building block of R, unlike in Python, is a vector. So when you do, let's say, for example, x equals 5, x is not going to be a primitive data type, as like in other programming languages, including Python. No, in R, x will be a single value vector or array with the value 5. All right? So then what is a list? A list can basically store any data container within it. It can store other lists, so it can be recursive, and it stores other vectors and other of all sizes, shapes and sizes. And when I introduce other data containers in future labs, it can store those as well. It's a very versatile function, list. It's a very versatile function. And they had it in R because they needed a way to basically allow complex results, complex data structures, right, to be used in different functions and different processes and different analysis. So they came up with this concept of a list. And here, I show you how we define a list, right? I mean, there's several different ways you can define a list. So this is one particular way we can create our own list. And within here, you can see basically I'm creating a list that has a vector called A vector called B, and a single vector value called C. All right? So basically, it contains this vector, that vector, and this vector. If I were to simply copy this, that was clean. You'll see over here, you have something called L1 list of 3. Click on the arrow, and it'll break down for you what are the different data containers within that list. And it's showing you right there. Integer, number. All right, integer, number. All right, don't get too hung up on why this is an integer and why it's a number. It's a thing behind the scenes in R, what's happening. Okay, so how do I play with this? Well, there's several different ways to play with this. With a list, if you type in the list name, and then you type the symbol $, see what happens? After the $, this drop-down list comes. And basically it's asking you, hey, okay, cool. This basically means show me all the data containers within this list. In this case, there's 3, A, B, and C. So just pick whatever one you want. You process it, and it gives you the values of that particular data container. Right? So this is what that $, means. A $, allows, after a list, allows you to choose a particular data container within the list. Another way to do this without the names is the double bracket system. If I do like you've worked with single brackets with vectors, with lists, it's a double bracket system. So if I do bracket, number, close bracket, it gives me the first data container, all right? Or I can choose the second data container, 135, or subsequently the third one, right? Now we can get slightly more fancy, right? We can get slightly more fancy. What if, now remember, my first data container is a value 54321, all right? It's a vector 54321. What if I just want the third value in the first data container? All right, the third value in the first data container. How would I do that? Well, you could do L1 $A bracket 3, and it gives you the third value of the first data container. Or what you could also do is L1 bracket 1, and right after the double brackets, single bracket 3. You see that? It's kind of getting a little in there now, right? But here, you basically have your double open bracket, close bracket that defines which data container within the list you're looking at. And after that, immediately after that, you have your open single bracket, close single bracket. It tells you which element or elements you're looking at. So here I'm looking at just the third value, or I can also do something like show me the third, fourth value, which is 3 and 2. Alrighty? And I can go even take it a step further and say, hey, I want to change the values, this third and fourth value of the first data container within the list to be 100 and 200, right? Notice I'm using the C function again to define two values that I want to be changed, or to two values to be the new values. And when I do this, you will now see, right? You will now see, if I just type in all of L1, you will now see that the third and fourth value have become 100 and 200. All right. And notice when I typed in L1, it separates either data containers by their names, and there's also a little dollar before it, just like there's a dollar over here. And that, again, that dollar symbol is basically telling you, hey, this is a data container A. Here's its values. This is data container B. There's its value. Here's data container C. There are its values. That's what that dollar means, right? And you'll see that dollar again, that dollar notation again, when we start messing around with tables. All right. So at this point, I've shown you all the basics of R. Some concepts you've understood, some concepts you didn't. But don't worry, in the practice sets, you're going to know what you get, what you don't get. And again, like I said before, a little bit of practice with this stuff. I didn't necessarily type out everything, but you should go ahead and type out everything and play with it. Why? Look, if you're an experienced programmer, then by all means, just skim it, the information. If you're new to programming, the only way to truly understand programming is to make mistakes and fix those mistakes. And you can't make mistakes if you're not typing. So please, new beginners, you must be typing this stuff and making every possible mistake there is. Right? That's how you learn. That's how we all learn. All right, so ladies and gentlemen, this finally ends the third video of the introduction. I apologize for how it was piecemealed, how it was broken up. And this finally ends the introduction. And I'll see you guys next time on the videos for, I believe, the first lab. All right? All right, have a good day, or the next Q&A session. Have a good day, guys. Have a good day, guys. Bye-bye.